All right, okay, so welcome back, everyone. So today it's my pleasure to welcome you, Huang, who will be talking about deep learning for critical transitions. Yeah, thank you.
Okay. Thank you. Thank you for your invitation. Yeah, I'm very happy here to talk about our recent work about using deep learning to predict rate-induced tipping points. Yeah, I'm a postdoctor from Technical University of Munich, and this work is actually a cooperation study with my colleagues Sebastian, Peter, and Nicholas. Yeah. Firstly, I want to give a very brief introduction about the tipping points, especially in the climate field. Yeah, but I estimate maybe most of the audience, you already know a lot about tipping points. But here I would start from the Earth energy balance model. This is a very important, also very famous, basic uh, physical conceptual model for the Earth climate understanding, and also sometimes for the simulation. But if we perform the simulation on this energy balance model using different solar radiative forcing, this is the so-called control parameter rho. And if we change increase or decrease the control parameter and along the time, then we could observe we will observe the abrupt transition of the Earth's climate from a warm climate state to a cold warm climate state. But it's also possible just to transit back back to the warm climate, but just along the different pathway. But we notice here the transition along the time is very is just suddenly transition, not gradual transition. But here firstly I would like to use a very simple example from the our realistic life to explain the abrupt transition. Here I take I just noticed some pictures for the Swiss Grindwald Glacier. Maybe over 250 years ago, from some pictures over that time, we noticed there is a lot of glacier during summer. Even during summer, over the glacier, over the Grindwald mountain foods, uh, even until 20 years ago, the mountain foods, there was still a lot of glacier and ice there during summer. But until most recent 10 years, this glacier, this ice over the mountain foot disappears suddenly. It's very fast transition from the ice to just to the board rocks. But yeah, and and the local people also already notice this phenomena, and they really want to protect this beautiful glacier over the mountain foot. But this is picture I take from my camera the past September. I noticed the local people really tried a lot. For example, they built some dam. They are trying to build construct some bedrocks for this glacier and protect them. But actually, this does not really work for the avoid the shrink of the glacier. This means maybe in one generation, in our whole generation, it's really hard to recover this glacier. This is also a truth for the tipping points. This could also happen for a lot of climate subopponents. Uh, uh, components, for example, like the Antarctic ocean circulation, also the Greenland sea ice, also for some vegetation, like the Amazon forests. This such a transition, abrupt transition and irreversible transition would be very possible for this nonlinear system. So that a central target of our part of our climate people is to anticipate the tipping points and access tipping points risks behind the a specific climate subsystem. Actually, here I would we notice we could have three methods to anticipate tipping points from the current condition, but usually the physical based researcher would consider maybe we could find out the physical equations of a specific subsystem, and then we could recover the dynamical trajectory or the phase space of this dynamical system. Then we can construct such a bifurcation diagram for the interested system. Then we can directly observe the the critical threshold for the tipping points, like the here we can find usually for a bistable state, a bistable equilibrium state, we could find two critical threshold for the forcing values. Then we can estimate if the system will approach to the tipping points. But usually this method does not really work well because it's really hard to recover the whole equations or dynamics of the realistic system, especially like the climate system. It's really hard. So most recent years, scientists also find some alternative way. It's called the critical slowing down. Maybe you already heard about it. That is, we can really have the observational time series of the interested system. For example, here it's a Greenland sea surface temperature from the paleoclimate records. And here, based on the time series, usually we could make a linear assumption when the system is around its equilibrium fixed point. Then we can take this approximation equation. Then based on the damping parameter lambda, we could estimate if it were undergo at tipping points. The damping lambda, damping parameter lambda, when it's smaller than 0, it means the system will be stable. But if lambda increase anterior to 0, it will approach to its critical threshold. Then, if lambda continue increase, this also means the external forcing will increase, and the system could be unstable, and the tipping points will happen. But usually for the lambda estimation, we could make use of some statistic metrics like the autocorrelation of the time series segments, and also usually the variance of the time series segments. For example, here, based on this Greenland sea surface temperature records, every time when there is an abrupt transition, we can observe a increase in the autocorrelation and also the variance of the time series. This is a precursory signal of the bifurcation tipping points. Of course, recent years we also have the third way from the data science perspective, based by using the deep learning neural networks, we can also construct the early warning signal of the tipping points. And here, based on the Thomas Berry's first paper about this direction, we can find that critical slowing down indicator and both critical slowing down and the deep learning indicator can make prediction for the bifurcation tipping points very well. And this is good for our tipping points and also climate prediction communities. But most recently, some scientists just noticed some different thing. It's based on a modeling research on the Atlantic ocean circulation simulation experiments. Usually, we can define some safe space, like when we perform, when we will know we have the global warming as external forcing to the ocean circulation. But when the external forcing increase, but if it has not reached a critical threshold, then this means our climate system is safe, is stable. Tipping points will not happen, and usually we can define a distinct boundary for the safe operation space between the stable climate and the bifurcation tipping transition. But something different was noticed when Johannes Luhmann when they researched on the AMOC simulation. Usually we can construct such a bistable equilibrium state diagram. And we can understand it using the traditional bifurcation theory. But when Johannes and Peter, when they perform the different forcing rates on the AMOC simulation, that is the freshwater forcing from the sea ice, when they use different increasing rate of the forcing, specifically when they increase the forcing rate, like a very fast forcing rate, then they notice the AMOC state would reach the tipping points much earlier than a bifurcation tipping points. This is out of blue, and yeah, this is caused by the rate-induced tipping. And this also could happen for a lot of other nonlinear systems. But basically, around 10 years ago, some studies already from the mathematicians, they already realized maybe there will be 3 kinds of tipping for the nonlinear systems. Usually, the usual one we talk about is bifurcation-induced tipping points. This means under the slowing, changing external forcing, the attractor basin of the system would change its shape, and the equilibrium state the dynamical state would be shifted also by just with external forcing. Then it could change to another state. This is bifurcation tipping points, but there is another two kinds of tipping, that is noise-induced tipping. That is, there is no very strong external forcing, but just some noise perturbations or noise forcings. But basically, the attractor basin of the system could keep its shape, and just because the noise forcing could drive the system state from one equilibrium state to another equilibrium state. This is the noise-induced tipping. But for the rate-induced tipping I mentioned in the last slide, it's caused by the fast forcing, specifically a fast forcing. That means that when the forcing is very fast and comparably, the attractor basin, maybe its shape has not been changed a lot, but the equilibrium, the system state cannot attract its original equilibrium state anymore, then it can just very easily shift to another equilibrium state or just collapse. This is a rate-induced tipping, and the noise and rate-induced tipping are just out of blue of the bifurcation tipping diagram. And what does this mean for our climate system? We know for the future scenarios, people always and the society always worry about the global warming gas emissions, and they already designed different emission pathways, trajectories pathways. This means we could have various very different forcing rates in the future scenarios. But this means our climate could have much more complex tipping risks from the noise-induced tipping and rate-induced tipping diagram. Maybe this means even we have not reached bifurcation tipping points, bifurcation tipping points threshold in the future scenario, but our forcing is very fast, then it's also possible for our climate lose its stability. So we really want to also make some prediction for make some improvement for the prediction of rate-induced tipping, this out of blue tipping points. But this is really challenging because based on most recent studies, a series of studies, we already realized it's really challenging. Firstly, the dynamical equation, usually the dynamical equation of our realistic system is unknown, and also we can't really know the critical thresholds for the rate-induced tipping. Secondly, we also already know critical slowing down does not necessarily work for the noise and the rate-induced tipping because basically the critical slowing down is based on the linear assumption around the equilibrium. But in this case, in the rate-induced tipping case, this does not necessarily hold. Thirdly, usually for the realistic system, the rate-induced tipping and noise-induced tipping, like the weather perturbations, also like some internal variability of climate system, it could they usually happens together, just work in a concert to our climate system. Fourthly, it's also very hard to generalize to get some experience from the ensemble simulations of climate models, then make prediction on some individual trajectories. In the following slides, I will explain these two, the third one and the fourth one, fourth points in very detail. What I mean the rate-induced tipping here, it's it could be explained by these three panels. Firstly, when we perform very slowly changing forcing on the system, perhaps the system, the dynamical state as the red dots, it will it will always attract its equilibrium state, fixed point, and the tipping point will not happen. But if we shift the attractor basin of the system very fast, potentially this red ball could not really track its original attractor basin and just tip to another state. This is possible, but in these two cases, there are no noise. There are no noise perturbations. But if we consider in addition consider the noise perturbations like some weather perturbations, some internal variabilities. In this case, even though the forcing shift rate is not so fast, but the rate-induced tipping can still happen. This is what I mean, the concept of the noise and the rate-induced tipping. This could be very realistic for more closer to this could be closer to our realistic cases like the vegetation and also climate systems. And here we just take three typical dynamical system, the saddle node and bolting and compost boom system, and perform the fast forcing external forcing on these three systems in the specific respectively, and also perform also add some noise perturbations to them, and then we can get different simulations. Even, for example, if we first have a look at the saddle node system simulations, we always keep the same forcing profile, and also the same forcing rate, same forcing trajectory time series. In this case, if we have different white noise perturbations on this system, and the trajectory of the system time series will be very different. And here we notice some of them were tip, but some of them were not. And we also make a statistic for the tip time, like when these red time series largely significantly diverge from the non-tipping category envelope, then we can define the tipping time. And you see here, the tipping time is the uncertainty of the tipping time is really large. We cannot really estimate the tipping time simply from the equations. Even though now we already know the physical equation, mathematical equation of this saddle node system, but we still cannot really estimate the forcing the thresholds of the tipping rate-induced tipping, and this would be similar for the other two systems, and of course this is similar phenomenon are already observed by Johannes and Peter in the AMOC simulations. So here we just want to make some prediction for these tipping points. We just now I mentioned three main methods. The first method, it does not work here. The found threshold values, but it does not work here. And then we take the critical slowing down indicators, the autocorrelation, and also the variance of the time series here. Firstly, if we classify the simply make a category, two categories for the R-tipping scenario and non-tipping scenario for our ensemble simulations time series or samples, then from the time series trajectory before the R-tipping happens, we cannot find out the distinguish the tipping time series in visual observation. And then if we calculate the autocorrelation and the variance of the two categories, then we will find there is almost no visual difference for the R-tipping and the non-tipping categories. But of course, for the deep learning methods, we can distinguish them very well. But I will introduce the third indicator later. And yeah. But still we still believe maybe we can find out some evidence of the potential predictability of the R-tipping from the raw data. That means here we have the time series, or we already have the time series of tipping and non-tipping categories. Then focus on the specific leading time before the tipping happens. For example, here, if we take the 100 time steps before the tipping and make a slice for the two envelopes, then we can get a PDF, a probability distribution of these two categories. And we can really observe some difference between these two categories, but in practice, if we really want to make prediction based on this, based on the visual difference from the probability distribution, then it will make you disappointed, because but I will introduce the prediction results based on this probability distribution later. But yeah, I can tell you here it does not work well. And also we observe we also have a look at the distribution difference based on the autocorrelation indicator and also the variance indicator. And indeed we can observe some difference in the in the PDF, but still it cannot really help us to make prediction for individual trajectories. That means basically we can, if we observe we already know the envelopes of the tipping and non-tipping trajectory, but hopefully for individual trajectory time series, we can also make the prediction. But yeah, this is what we want. Just get some experience from the ensemble simulations and then make the prediction for a specific time series. This is also usually what we did for the climate in the climate studies. So here, let's move to the third indicator, the third prediction method, the deep learning method. Here, we just take the time series from the tipping and non-tipping categories, and then, for example, here we just pick up a time series segment, just with a certain forecast lead time to the tipping points, then feed them into the neural networks here, and then hopefully we expect the neural networks can give us the classification results. It's basically the R-tipping probability and the non-tipping probability of this time series. Here's the neural network. For the neural network architecture, we took a very simple architecture based on the well-known CNN architecture neural network. Here we take two CNN neural network and then combine them with a fully connected neural network. This is very simple because we want to, yeah, we expect if the very simple neural network architectures can work for the rate-induced tipping prediction, then hopefully the much more complicated architecture will also works. So here, let's see the prediction results. Here, firstly, let's have a look at the saddle node system time series. Here, I only present two time series of this from this system. Here, the red one is for the tipping time series. Blue one is the non-tipping case. And here, if by fit them into the trended neural networks, then the neural network could provide us the indicator exactly the R-tipping probability of this time series at different forecast lead time. And we notice when the time is approached to the tipping points, then for the non-tipping case, its tipping probability will continuously increase until 100%. But for the non-tipping case, its tipping probability will continuously decrease. And these indicators for these two time series just develop along two opposite directions. But for the autocorrelation and the variance indicators, yeah, they both give the increase signal, but we cannot really infer if there will be a tipping points for the blue or red time series before the tipping happens. This similar phenomena conclusion can be also found from the Bouting system and composed boom system. Yeah. Here,
Could you talk a bit about the training data that's used for the model? What kind of
yes.
training data was used?
Yeah. The training data basically it's here. If we have a look at time series in this slide, the first panel here, the we yeah this envelope is made from the a lot of time series. It's ensemble simulations. This means here we perform the same external forcing on the same system, but using different white noise realizations, then we can get different get different simulations. This is just like the climate, also like the climate simulations. We give the different perturbations, then we can get different trajectories. This is then our data sets source, and the training set is basically we only have two. This is a classifier. Neural network is a classifier. We only feed two kinds of data. One is tipping data. Second is non-tipping data, and we also label them as 0 and 1 respectively. Then we can get the tipping probability, the classifier probability for these two classifications. Yeah, I hope this is clear to you. Yeah.
So it's climate simulation data that's used for training. Essentially, this model is capturing
separately.
the way in which those climate models identify the R tipping.
Yes.
Okay. Yeah. Thanks.
Okay. Yeah, you're welcome. But yeah, of course, here in current stage, the model which actually trained three kinds of model, each kind of model specifically for a certain system. For example, for saddle node system, we train the neural networks, but for the Bouting system, we will train a new deep learning model for its prediction. And but in the last slides, in the later following slides, I will also present the intermodal inter-system prediction. But here we can observe everything is clear, and we can understand the system and deep learning very behavior better in this way. Yeah. Here I would make some simple comparison between the three tipping between the CS critical slowing down indicator and then deep learning indicator comparison. Here we notice for the autocorrelation, when we perform the prediction on all the time series samples, then we can observe the for the deep learning indicator, it can always help us distinguish the tipping and non-tipping category with a considerable forecast lead time. Of course, here we also make estimate evaluation for the deep learning prediction. Actually, it's just a classifier for the tipping and non-tipping. But let's firstly have a look at the bottom panels. Bottom panels means the different color, the blue and red colors represent the testing dataset and the training dataset. Overall, the training and the testing accuracy curve are almost overlapped. This means our model is robust and maybe we don't need to worry about the overfitting problem. But of course, we also perform the cross validation, a lot of extensive evaluation on to check if there is any overfitting issue for the model, but the results all show the overfitting almost very weak here. And also we in the very beginning of when we have a look at the time series tipping and non-tipping time series, I mentioned we can actually make a very simple prediction based on the probability distribution of the tipping and non-tipping. And we create some very simple algorithm to realize the probability distribution based prediction method, and we compare it with our deep learning indicator here. And seems deep learning indicator have better accuracy than the visual observation on the probability distribution. Yeah. And in the following, I would like to introduce some very interesting phenomena based on our analysis on our trained deep learning model. Firstly, we want to discuss about out of sample prediction of deep learning, because this is very important for the data science. Usually we train our model on a specific some specific data sets, but afterwards when we met some new data resource, our model it would be dangerous for our model to make some make prediction on some unseen previously unseen data resource. So here we want to discuss about this point. Firstly, we test our model for the out of sample forcing rates prediction. That is, just now I mentioned the model I mentioned, trained model I mentioned just now is trained based on a fixed forcing rate. For example, here actually for the saddle node system, basically we can design different forcing rates for it. But when we train our deep learning model, we always use a fixed forcing rate. The forcing rate is just it can be controlled by the parameter lambda in the saddle node system. And yeah, here we only take a fixed forcing rate. It's 1.25, like this dashed line shown. When we trained it we trained our model, we will fix everything unchanged, and just let the just use the trained deep learning model to make prediction for other time series. The other time series are generated from the different forcing rates, and these forcing rates are unseen during the training phase. And here it seems it still work for other forcing rates, but it seems it could work for the out of sample forcing rate. So in the following way, we further train a new deep learning model for the saddle node system prediction. Here, we just take another fixed forcing rate like the panel D. In the panel D, we use another forcing rate and generate the data and train the deep learning model. Then use the trained model to predict the unseen forcing rates for other time series, like here, panel D. And here, if we compare panel A and panel D, the deep learning model are trained on different forcing rate, but the accuracy pattern are very similar for these two trained models. And for the in the panel G, actually this is we did additional experiments. We just feed all the forcing rate time series into the deep learning model. Then in this case, there will be no previously unseen forcing rate for the deep learning model. Then we compare the prediction accuracy pattern from panel A, D, G, and they looks very consistent. And this is for the saddle node system. And here also did the same thing for the other two typical systems. But for the composed boom system, we use different forcing rates, and we can get the same conclusion as the saddle node system. But for the bolting system, yeah, honestly here, it's really different for panel B and panel E when we use different forcing rate to train the model. And yeah, for this for this phenomena, we thought it's because bolting system basically it's a lot of it has a lot of complicated chaotic oscillations in itself. So in this case, like in panel B, when we train the deep learning model on a fixed forcing rate, for other forcing rates, the chaotic oscillations behavior is really different. We thought this chaotic oscillations will disturb the prediction of the deep learning model. But if we feed all the time series forcing rates time series into the model, train the model, and make prediction on the testing data set, then it can give us looks much more comfortable pattern in its accuracy. And yeah. Here, this means when we train, this is also important for us. In the future, if we want to train a deep learning model, we should consider for a specific dynamical system, its internal dynamics could potentially disturb the deep learning indicator. This need to be careful. Yeah. And then second analyze is for the prediction of the out-of-sample dynamical systems. That means for the three dynamical systems, saddle node, bolting, and composed boom, here we plot the autocorrelation function of the time series respectively from these three systems, and we can observe the there is some time scale separation between these three systems. This means the dynamics of these three systems are largely different from one another. But here we still perform a interesting experiment. For example, for the saddle node system, we train the deep learning model on a fixed forcing rate, a certain forcing rate from the saddle node system, then make prediction for other forcing rates, and also for the other forcing rates in the bolting system and the composed system. Let's look at panel A, B, C. This means we and we can still observe some skillful prediction, but although it's very close to the tipping times, but still this means hopefully this deep learning could make some out of sample prediction on make some skillful prediction under the out of sample dynamical systems. And here we also did the same thing for the other two dynamical systems, and it seems it's very interesting. Like for the bolting system, the deep learning model trained based on bolting system, it can work very well for the composed boom system. And this pattern, if we have a look at the pattern F and I, the bolting system's deep learning model can make very well prediction for the composed boom system, and the pattern are very similar to each other. This means although the dynamics are different, but it can still make skillful prediction sometimes. And yeah. Finally, we also train our deep learning model. Train a deep learning model includes all the forcing rates and all the time series from all the three systems, and then we call it a comprehensive deep learning model. Then eventually this comprehensive deep learning model can predict the can predict the rate-induced tipping very well for the three different systems. Yeah. Yeah. It's very close to the final slides, but yeah. Here I also want to introduce some interesting thing. It's a perspective from the explainable AI, but yeah. Basically, the explainable AI we could associate it with ridge regression. For example, consider if we have a ridge regression, we use a ridge regression model to fit based on a lot of explainable variables. Then for each explainable variables, we could have the feature importance based on the fitting efficiency of the ridge regression model. Here for the CNN model, it's the same. We just take the layer relevance propagation algorithm to extract the feature importance of each input data. This could just associate it with ridge regression feature importance this would be very similar diagram. But here, it's a prediction for the saddle node system, and just 30 time steps before the R-tipping happens. Then, if we compare the layer-wise propagation LRP score before for different time series for different point of the time series along the time series, then we expect to find out some precursor signal hidden in the time series segments at different time lead time forecast lead time. For example, here, if we compare the R-tipping and non-tipping categories of the for the LRP score, we can find it's very different, and specifically, we find two difference feature importance. One is very close to the tipping, the end of the time series segment. This is comparably easy to understand because this means the R-tipping probability are highly related to the current time step, the current time point of the system state, for the system state. But also we find a fingerprint. It's a fixed fingerprint around a time window that is 50 time step to 100 time step before the R-tipping happens. And we notice this peak. And for this peak, it's very interesting. We realize there must be some dynamical features can be already captured by the deep learning model. Then there is a peak here. So basically, for the model for the deep learning for the R-tipping for the R-tipping here, there are two elements for the R-tipping. One is the forcing rate. Second one is the noise perturbations. But for the noise perturbations, we checked it, but we didn't find any special thing related to this fingerprint. But for the forcing rate, we found some interesting thing here, because the time series here, they have different maximal forcing rates maximal. That is just now here for the forcing profile. If we calculate the difference time series of the forcing profile, then we can get the instant forcing rate. Also, yeah, it's instant shift rate also. Then we can we just make a composition and find some early R-tipping and late R-tipping. That means the early or late is comparably defined by the maximum of the instant forcing rate. For example, like the early R-tipping, the tipping time is very close to the maximal forcing rate. Usually for the in previous studies, people would think when the external forcing reach its maximal forcing rate, this is most dangerous for the most dangerous period for the system to undergo to have a tipping point. But here we find that it's relatively late to the maximal forcing. But we also find some other samples. The tipping time is much later than the maximal forcing rate. And here, if we have a look at forcing rate, it's exactly shares a common time window with the fingerprint here. Yeah. And finally, we also have a look. We also want to talk about something about the selection of the neural network architecture, because I mentioned we just use a very simple CNN, and somebody would argue, oh, why why just use a very simple CNN? It's an old dog, but I have to say the neural network CNN is very powerful, but it's simple. If we select a simple neural network architecture, then this could be helpful for the community to understand it. But here we also compare it with different just take two different neural network architectures like the LSTM and also the MLP or self-attention mechanism, and then make the prediction. This is the ROC curve of the prediction results. It seems CNN LSTM or the combination of LSTM CNN. This is exactly Thomas Berry ever used in his PNAS paper, and also compare with and also the self-attention. They have the comparable prediction ability. Maybe for the bolting system, it's chaotic dynamics really disturbs the performance of the MLP. But here, yeah, we anyway we could conclude that deep learning indicator actually is independent on a specific neural network architecture. We can in the future we can even consider a more comprehensive or complicated architecture like transformer or generative deep learning model to get maybe can get better results. But here it seems CNN is also works very well and it's efficient in computation. I also want to highlight some useful thing for the deep learning indicator. We know for the critical slowing down, it's always calculated based on the time series autocorrelation and variance. And this means we usually, even though we for a specific system like Arctic, like the an Atlantic oscillation, ocean oscillation, we could have a lot of multiple. We could have a multiple time series for it, but usually we can only calculate critical slowing down based on one of the time series. But here for the deep learning model, we can just simply add the add more explainable more dynamical variables into the CNN. Just simply add one additional channel, then we could make the prediction for by involving more dynamical variables. But here it seems for the bolting system, composed boom system, they also have a multiple dynamical variables. But if we include them into the deep learning prediction, it seems it's comparable to the a single variable based indicator. This is the last slide, and it's a short summary, but I really want to talk something here. This could be useful for our future work. Firstly, we know the deep learning can advance our ability to predict rate-induced tipping and noise-induced tipping, and then we can just make use of the experience of ensemble realizations and just apply them into the inference on individual time series. And also we find the deep learning model can have good transferability across different out-of-sample forcing rates and out-of-sample dynamical systems. But of course, if we train all the models together overall, we must get a very comprehensive deep learning model and very powerful. But in the future, it's promising for us to predict tipping across critical forcing value. This is a bifurcation tipping diagram, and also in addition, the critical forcing rate, and then we can, hopefully, hopefully compared to the critical slowing down, we can have much more comprehensive early warning indicator. Also, make use of the explainable AI algorithm. We could discover more fingerprints of the tipping points for some specific systems like the Antarctic ocean oscillations. This is very wishful, and we really want to further focus on these points. But of course, there is still open question here, because just now the tipping early warning indicator is based on the tipping probability. It's basically it's a static metric, but of course, alternatively, we could also have a tipping trajectory prediction that is stand on current climate. Maybe we also want to predict the time serial time evolutional trajectory in the future scenario, and this is a tipping trajectory, but currently in our deep learning model architecture, this is not unachievable. But in a very recent paper published in physical review research, and also out in last month, and they already tried to do something along this direction. But we really hope this all the progress could help us to help us in serve for the tipping points community. Yeah. This is my email if you are interested, and just feel free to contact me. And also, last week our paper was published out in Nature Machine Intelligence, and if you want to know more details, you could also find more in that paper. Thank you very much. I think I'm done. Thank you for your time.
Yeah, thank you very much. Thank you. Any questions or comments? Yes, I have. Yeah.
I'm assuming you mean me.
Yeah. Sorry, I meant Louis. Yeah, sorry.
Okay, yeah. Interesting talk. I'm aware of a recent paper by Yingqing Lai of the Arizona State University and his group looking at the critical point at which a crisis happens in a chaotic attractor as you vary a parameter in the system.
Yes.
And they did this learning of that using a reservoir computer.
Yes.
And they did a pretty good job of telling where that was going to happen. Unlike yours, there was no noise on it, that I recall anyway. However, they did miss, they could not predict a window in the chaotic system. I'm wondering if you have tried a chaotic system, something like that, and tried to predict a bifurcation, and whether you've looked into using reservoir computers rather than a neural network.
Thank you. I think this the paper you mentioned exactly the paper here.
Okay.
I point here. We also already noticed it's very amazing. Firstly, for your question, let's focus on your questions. Firstly, for our deep learning model, CNN-based indicator, we have not tried for the bifurcation tipping, but the reason is this is already done by Thomas Berry. He has a publication on PNAS. It's on 2021, and he already demonstrates using LSTM plus CNN architecture here can achieve very nice prediction results for the bifurcation tipping, even for the I mean I know maybe you mean a specific chaotic system like the bifurcation in the Lorentz 63 system. Maybe it's, yeah, I noticed in Chen Lai's group, they also have a paper about this point, about this direction. But
Right.
yeah, thank you. We will consider about this a specific chaotic system, but although we have not tried, but I trust, I would believe CNN could work for it because here we have the bolting system. The bolting system itself is already very chaotic, have a very a lot of have a various chaotic oscillations in this bolting system. And so here our model works for bolting system, then I would believe it can also work for the Lorentz system.
Right.
But thank you very much. But
Yeah, thank you.
yeah, but also maybe for another question, maybe you related to your question is like the Inchen's group, they use reservoir computer is also very efficient in computation, and it can predict the trajectory, tipping trajectory, and but based on the recent two papers publications, we have a very close look at the paper. They already did a lot of nice work on the bifurcation tipping, but seems they have not done test if it also works for the rate-induced tipping. But yeah, I'm also very curious if it were what will happens when using reservoir computer predicts the tipping trajectory in a R-tipping diagram. This could be very amazing.
Yeah.
Thank you
you.
very much.
All right. Other questions? All right. Seems not. Yeah. Thank you very much, you for coming, and thanks again for the nice talk, and thanks all for coming. Yeah. See you next week. Yeah. Bye bye.
Yeah. Bye-bye.